Greetings. Welcome to Engineering Study, the Future of Chilled Water Plants and Waterside Economizers, presented by HPAC Engineering Magazine and sponsored by Johnson Controls. I'm Scott Arnold, Executive Editor of HPAC Engineering. Before we begin, a few words about our webinar technology. This newer platform allows you to be more involved with presentations, and more importantly, allows you to watch events the way you want to watch them. For starters, you can customize your console. You can move windows by dragging on the title bar and resize them by clicking on the lower right corner. You will notice a toolbar at the bottom of your console. The buttons there allow you to open and close widgets on your screen. Speaking of widgets, we invite you to get social. During our session, feel free to tweet your thoughts and impressions of the presentation to your followers using the Twitter widget. If during the presentation you experience technical difficulties, such as problems with the audio or the advancing of slides, please refresh your webinar console by pressing the F5 key on your keyboard. To download the slides, please click the folder icon on your screen. You can do this during the webinar without interrupting the presentation. We appreciate your feedback. Please click the red survey icon and complete the form at the conclusion of the webinar. Lastly, in the coming days, certificates of attendance will be emailed to audience members in attendance for the entirety of the event. Now, let's meet our presenter. As Global York Chiller Product Manager for Johnson Controls, Spencer Fuller is responsible for special projects and studies supporting York Global air-cooled and water-cooled chiller offerings. He travels the United States giving educational product and systems presentations. Previously, he held the positions of Global Product Manager for York YMC² magnetic bearing water-cooled centrifugal chillers, which saw him manage the global product line across 3 factories and launch a chiller capacity extension, and Chiller Solutions Product Portfolio Manager for North America, which saw him responsible for ensuring York air-cooled and water-cooled chillers met current energy standards and customer requirements. He is a graduate of the Virginia Military Institute with a degree in mechanical engineering, a lead green associate, and a member of the American Society of Mechanical Engineers and ASHRAE. Ladies and gentlemen, Mr. Spencer Fuller.
Thank you, Scott, for that wonderful introduction. And thank you, everyone, for attending this live webinar where we will be discussing the chilled water plants and waterside economizers. On the call today, I also have a team of people looking to answer any additional questions that you may have about the webinar and the content within it. We have a wide range of job functions in terms of the team supporting here, from product managers to product engineers to product marketing engineers, and we look to get all the questions answered in a timely fashion. So please feel free to submit any questions to the team here on the call, and we will be sure to answer them. So in getting started here, throughout this presentation, we're going to talk about a few key things. One being the YMC² and its capabilities and flexibilities that this current product has in the York product portfolio. We're also going to discuss the traditional chilled water system design, how it looks, and the downsides to today's chilled water system design. And then going into the new chilled water system designs, giving a view on its capabilities, the benefits, and how this new system functions properly. And then leaving you with thoughts to the future in terms of additional resources that you will have at your disposal, more about our products and accessories, and overall just getting the ideas of these new chilled water systems out into the market. So to start off, I wanted to get the audience a question and find out where we lie in our chiller knowledge. So the question being, what is the lowest entering condensing water temperature a chiller can handle? This is very important in today's chiller industry because the lower the tower water usually equates to an increased efficiency in the chiller. So we'll give it a few seconds and a few minutes to receive these results, and we will proceed on. And throughout this presentation, there will be questions and additional poll questions that we're looking for feedback on. Okay, looks like we got a majority of the results in. In viewing those results, it looks like everyone, or a majority of the people, are leaning towards 50-degree entering condensing water, when in fact the true answer nowadays is 36-degree entering condensing water. And this is going to be very prevalent to our discussion today, and being that the YMC squared chiller is the only chiller in the world that can utilize this low tower water. So just a question to the audience. Can efficiency numbers, when we're pertaining to the chiller itself, achieve numbers lower than a 0.1 kilowatt per ton? And that's a very efficient machine in today's standards, because that's almost approaching the theoretical efficiency of the chiller itself. So when we look at a traditional chiller nowadays, a constant speed centrifugal chiller, we see part load values in the 0.4 kilowatt per ton range. And as we begin to add further advancements to our products, such as variable speed drives, even the use of magnetic bearings to our chillers, we start to bridge the gap between 0.3 and even sometimes 0.2 kilowatt per ton. But what the YMC squared has done now is taken a huge leap in chiller technology and provided efficiency numbers sub 0.1 kilowatt per ton. I'm referring to as a 0.07 kilowatt per ton in our industry. And that's the lowest efficiency number within our market. And how this is possible, we will get to in a second. But I want to further take you through the operating map and how the YMC squared is able to achieve these efficiency numbers. So in looking at the unloading curves for these YMC squared chillers, here's a graph. We have the load of the chiller on the x-axis from 20% to 100%, and the kilowatt per ton, the efficiency value, on the y-axis. So if I begin to plot my unloading curves as my chiller unloads throughout the year, we're looking at entering condensing water temperatures of 85, 75, 65, and even 55 degrees. 55 degrees entering condensing water being kind of the industry norm across manufacturers. But I want to draw everyone's attention real fast to the black dots on the top three lines. These black dots are referring to the IPLV points that ASHRAE 90.1, or excuse me, AHRI 550, 590 equates part load efficiency to. So at 85 entering condensing water, it equates at the 100% mark. At 75%, it utilizes 75 degree entering condensing water. And at 50 and 25%, they're utilizing the 65 degree entering condensing water efficiency value. But as you notice, the 50 and 25% utilize the same entering condensing water. It does not continue to unload with 55 entering condensing water or even lower down to 36 entering condensing water. So what that does is the IPLV is kind of the miles per gallon on a car. It's apples to apples comparison across the industry, across manufacturers, that allows owners and engineers to set aside one chiller versus another and look at how the efficiency plays out in the part load range. But we like to bring real-world efficiency and real-world energy to your doorstep. And because around the world, tower waters below 55 degree entering condensing water are achievable in today's market. So let me look at 36 entering condensing water. Since we said the YMC squared can now utilize 36 entering condensing water, what does that look like in relation to everything else? So the yellow line at the very bottom is just that. And if I compare the full load part, looking to the far right at 100% and comparing the 85 degree entering condensing water efficiency value to the 36 degree entering condensing water value, it's a 66% reduction in efficiency. And that's huge. And that truly is out of this world. And if I continue to follow that yellow line to the 40% mark, that efficiency value is that 0.07 kilowatt per ton that we mentioned before. And that is incredible from a single component, the chiller within a mechanical space. And evaluating the chiller altogether, I mentioned before real-world energy and real-world efficiency. Well, Mother Nature doesn't inherently give us just 85, 75, 65, 55. It gives us all those temperatures in between. So I want to show that. With our YMC squared here, a 500-ton mag bearing, The IPO value being a 0.307 is a very efficient machine alone. And again, the IPOV only correlates to 85, 75, and 65 degree tower water. I would like to show you the efficiency at every other point. So off to the left of this grid, we have the condenser entering fluid temperature, 85 degrees all the way down to 36 degrees. Across the top is the load profile, so 100% all the way down to 10%, and all the efficiency values that are pertaining to those specific points. And I want to draw everyone's attention to this bottom right quadrant. So typically with a central building or an office building, it will incorporate a waterside economizer to where it will become important in the winter months when it drops below 50 degrees outside. Well, now I'm saying my chiller can now operate where a waterside economizer typically does. And that's what this grid is pertaining to. And if I zoom in on this grid, looking at 60% down to 10% and 45 degree entering condensing water down to 36, look at these efficiency values. At 50%, providing 250 tons of cooling, the chiller is consuming approximately 22 kilowatts. Now I have to keep saying this number again, is 22 kilowatts. Typically when we deal with chillers, it's hundreds of kilowatts. And now we're in tens and 20s of energy consumption by the chiller itself. And the 0.089 is just one of the efficiency points that are mentioned here on this graph. I also see 0.071 for this 500-ton chiller. And again, this is the only chiller in the world that can operate continuously with 36 degree entering condensing water across the load line. So another question to the audience. Just a general question, what has a greater impact on chiller efficiency? Is it the load of the chiller or the lift of the chiller? Lift pertaining to the amount of work that the chiller has to do or overcome to produce the cooling tons for the building. And we'll give it another 30 seconds to receive these results. So it looks like a majority of the results are in. And looks like everyone, or majority of the people, are leaning towards lift. And that is the correct answer. The lift of the chiller has the greatest impact on the chiller efficiency. And what that looks like is we're going to go back to our unloading curve for this YMC squared chiller. If I follow one of the lines, let's start with the 85 degree entering condensing water. And I begin to move left as the chiller unloads. Yes, my chiller does become more efficient to a certain point. But if I step down from line to line, taking the 85 degree, dropping it to the 75 degree, that's a lift reduction on the chiller. And as you can see, that's a greater impact in the chiller efficiency. So again, getting back to that 66% reduction in efficiency from 85 degree at 100% load to 36 degrees at 100% load. It was a 66% reduction in chiller efficiency. But what about the traditional chilled water system? You know, we talk a lot about what's in today's market. And a majority of these plants have a base chiller, if you will, whether it's 1, 2, or upwards of 10 chillers. And usually there is a waterside economizer associated with the plant. And I will interchange words such as free cooling heat exchanger or plate and frame heat exchanger in place of waterside economizer. But throughout this study and the analysis of this engineering study, when I mention the word base chiller, what I'm referring to is a chiller that meets ASHRAE 90.1 Path B, which is the variable speed drive portion of the efficiency numbers. And those numbers are reflecting a full load of 0.585 and an IPLV, the integrated part load value, of a 0.380. And if I plug these two components into my schematic, here's my simple layout of a mechanical system. I have my chiller, my waterside economizer, my building load, of course, and then my cooling tower for heat rejection. But how a traditional operation works is typically in the summer months, I'm going to be 100% mechanical cooling, if you will. I'll be running my chiller to supply the cooling tons needed to make our air-conditioned space cool. In the winter months, I can do this. I can run or utilize my Waterside Economizer, turn off my chiller, turn off that electrical load, and just achieve the cooling tons based on this plate and frame heat exchanger. But my question to the audience is, those shoulder months, whether I'm going out of summer or going out of winter, what happens? Well, I might not be able to utilize my Waterside Economizer to achieve 100% building tons needed to make everyone cool in the air-conditioned space. Therefore, I will have to run my chiller. And what we're proposing, or what we're asking, is what if I could remove that component? What if I could take that Waterside Economizer out of the system? What will it do? Well, now that the YMC Squared has the functionality and the flexibility to achieve 36-degree entering condensing water efficiently, we can remove Waterside Economizers. So going back to the traditional chiller operation, I pulled out my Waterside Economizer now, and I'm just looking at a plant with a chiller. So based on AHRI 550-590, the evaporator is going to supply 44-degree leaving chilled water to the building, and that's at a flow rate of 2.4 GPM per ton. On the other side, the condenser barrel, I'm going to receive water from the cooling tower at 85-degree entering condensing water with a flow rate of 3 GPM per ton. And this is going to be my design conditions typically. It may be different in other markets in terms of how you're designing your buildings, but AHRI, again, gives us that baseline to compare manufacturer to manufacturer across the industry. But since I can utilize that cold tower down to 36-degree entering condensing water, what happens now? Well, I'm going to take my 85, drop to 36, because throughout the year, Mother Nature is inherently going to give us colder weather, and I can get colder tower water. So here's what 36-degree entering condensing water, the schematic, looks like. What's happening with my chiller now? Well, it's now operating in what we classify this as an inverted duty, to where the entering condensing water is actually at a colder temperature than the leaving chilled water. And this is, again, is the first chiller in the world that can operate this way. And what it's doing is it's really minimizing the amount of lift on the chiller to almost nothing. And with 36 entering condensing water at the design flow rates, it's still maintaining a 10-degree delta on the condenser. And again, it's all about minimizing lift. So for this setup, I do not need a head pressure control valve or slowing down my condenser flow rate to ensure head pressure within the condenser to make my chiller work. My chiller will protect itself, and it will operate in this inverted mode to consume the least amount of energy possible. And how is this possible? How is this one and only chiller able to achieve this? Well, the first being oil-free operation, meaning that the YMC Squared chiller is a magnetic bearing chiller with zero oil in its system. So it eliminates any concerns about oil return back to the compressor that a traditional chiller may see. As mentioned before, it is a mag-bearing chiller, and this is a permanent magnet motor and active magnetic bearings. So essentially the driveline is free-floating, and how it's adjusting to wide range of conditions and capacities is all based on speed. No more pre-rotation vanes or inlet guide vanes to achieve a specific capacity. The outstanding performance. If these chillers were operating at a 0.3, 0.4 like the traditional chillers were, then removing a Waterside Economizer may not be in our interest. But since this chiller, the YMC Squared chiller, is achieving a 0.07 kilowatt per ton in its operating map, it allows us to now evaluate removing the Waterside Economizer. And lastly, the variable orifice. And although this is one of the smallest components on the chiller, it is one of the most important components on the chiller. And what the variable orifice, as seen in this picture, which is a butterfly valve used on the York centrifugal chillers, it's going to ensure enough refrigerant flow from the condenser to the evaporator. Again, it's all about head pressure and making sure that the refrigerant flows properly from the condenser through the orifice to the evaporator. So it will open and close depending on the pressure differential needed to overcome the set of conditions seen outside. So this is giving us the ability to utilize the 36-degree entering condensing water efficiently. So now we covered the efficiency of the YMC squared chiller and having that out-of-world experience in its capability. We've looked at a traditional chilled water system schematic, very simple design, and we looked at removing and what we brought into the discussion of inverted operation. So now let's go into an engineering study that was performed by Taylor Engineering on the West Coast. They performed this engineering study for various load profiles, meaning different building types. But for this presentation, in the essence of time, we're going to focus in on an office building with two 500-ton centrifugals, meaning it's a 1,000-ton office building with an internal base load of about 200 tons. And every building has some sort of base load, whether it's from the lights, the computers, the data server racks. There's always some sort of internal load in an office building to some degree. We also incorporating the use of variable speed evaporator pumps, so variable primary flow on our evaporator side, and constant speed pumps on our condenser pump side. And the reason for that is it's all about lift. Again, we get back to the essence of lift. Reduction in lift gives us the most bang for our buck in chiller efficiency. So if we adjust the flow rate of the condenser flow, like a head pressure control valve will do, or VSD pumps on the condenser side, it will negatively impact our chiller efficiency. So we want to maintain that chiller efficiency as high as possible. And then lastly, optimizing my tower control. So utilizing a VSD fan on my tower to ensure I'm not spending as much electricity as I need to get the most efficient plant possible. So with these four primary components, the pumps, the tower, and the chiller, Taylor Engineering then set out to optimize the system efficiently to provide a solution that is going to save the end customer the most money. So now that I have my building, we then evaluated at 3 different locations: Dallas, Chicago, and the San Francisco Bay Area. And for those located internationally, all these cities, these 3 cities can be adjusted to around the world conditions. These 3 cities will see conditions that Australia, South America, Europe, and even China experience throughout the given year. But here is the ASHRAE 90.1 zoning for the United States. But keep in mind that this analysis can be adapted to the international locations as well. So now that we have our study, let's look at the results. So let's first focus on the annual energy cost savings. So look at the energy spend between 2 plants, one with a Waterside Economizer, one without. So some of the modeling assumptions. So for Chicago, Dallas, and San Francisco Bay Area, we locked in a flat electricity rate. We then utilized ASHRAE 90.1 modeling assumptions and techniques that were applicable for all markets and can be found within ASHRAE 90.1 for verification. Taylor Engineering then simulated the chiller load profiles within eQuest, which is a very popular simulation program among engineers. And then we used the theoretical optimal plant performance approach in obtaining the chilled water plant performance. And with this, and these assumptions and these results, it equates to a base chiller with Waterside Economizer providing this much annual cost to the end user, meaning that this is the energy use of the pumps, chiller, power, all together. And again, base chiller referring to the chiller that meets ASHRAE 90.1 Path B and those efficiency values of both a 0.585 and a 3.8 on the part load. And if I compare that to my YMC squared chiller setup, my YMC squared chiller setup does not include a Waterside Economizer. So we'll talk about first cost here in a moment. But the YMC squared chiller plant does not have the Waterside Economizer within its schematic to where the base chiller does. And looking at these annual energy cost savings, in every case for this office building, it was more efficient to have the YMC squared chillers without the use of a waterside economizer within its plant, upwards of 10%. And if I focus in on Dallas for an example, it's saving $10,000 a year approximately to go with the YMC squared plant schematic. Again, not including waterside economizers. And that's for 1 year. If I look at the life of these chillers being 30 years, that's $300,000 associated with the energy cost savings from going from a base chiller with waterside economizer to a plant containing YMC squared chillers. So we're going to discuss a lot about if you could save $500,000 in your building, would you do it? This being part of it, $300,000 in annual energy cost savings over 30 years. But the cost, nothing's free in this world. If I take Dallas again as the example, and I look at the cost of the waterside economizer system, I have the plate and frame heat exchanger, the installation, piping, and accessories, meaning bypass valves, and the controls. It's approximately $200,000 in upfront costs and capital expense that the owner has to pay for right off the bat. And this does not include routine maintenance either. We disregarded routine maintenance in this study for the sole purpose of, depending on your water quality and where you're located at, it could vary your routine maintenance costs with the waterside economizer. So we wanted to take that variable out of this analysis and just focus on fixed cost items that you would have to purchase in your plant. So $200,000. And if I look at this across the 3 cities, we took cost estimates provided by contractors and suppliers for these plant configurations for the waterside economizer. We then adjusted based on the city cost indexes from the RS means mechanical cost data. So in Chicago, it was about $150,000, where in Dallas, it was a little over $200,000. And that's the cost associated with the waterside economizer. If I then pull in my annual energy cost savings that we just discussed, I'm now providing a plant that's more efficient, saving me on utility costs throughout the year, and it's cheaper upfront costs because I don't have to have the costs associated with a waterside economizer. So in looking at those 2 variables, it's an instant payback to go with the YMC squared plant setup, meaning I no longer have to evaluate a waterside economizer in my system. So again, let me back up real fast. These first costs and energy costs associate with $500,000 across the life of this mechanical plant being 30 years. And that's a lot of money. So we then looked at the annual energy cost, the first cost, the plant setup. What are some other advantages that this setup brings or this design brings to the table? Reduced floor space. It's going to save you on your footprint within your mechanical plant. So that's room for expansion for more chillers or just more workspace for the maintenance. Fewer water leak points. Because I don't have the plate and frame heat exchanger anymore, I don't have the piping associated to that waterside economizer. So it's less leak points, less chaos in your mechanical plant. Routine maintenance costs. Again, we pulled that out of the analysis, but that is something to consider. Based on your water quality at your mechanical plant or city, it could impact your cost savings and provide routine maintenance that you need on your plant. And here's a picture of a plate and frame heat exchanger that is dirty due to the poor quality of water. The last one's a very interesting concept. It's looking towards the future and accommodating for an increased building load. And what I mean by that is we've been discussing a lot about new construction. Well, what about the case where I'm replacing an existing chiller? Or my building load increased, whether it's a new wing to a hospital, more data server racks in my office space, or I'm just now my building load occupancy level increased. Well, my building load increased as well with that. And generally, my waterside economizer was not designed for that increased load that the future brought on that building. So what do I do now? Well, now I have to run my existing chiller to accommodate for that increased load. But since an existing chiller doesn't have the functionality that the YMC squared brings to the table of utilizing 36-degree entering condensing water, the 2 components do not work in conjunction with each other very easily. But if I replace that existing chiller with a YMC squared chiller, I'm now able to accommodate for that increased building load. And what is happening now is, now in those winter months or those shoulder months, I can utilize the Waterside Economizer, providing enough free cooling as much as possible as the weather permits. And then to make up the delta, I can run my YMC squared chiller. Because it can unload to 10% and because I can utilize 36-degree entering condensing water, the two components now work in conjunction with one another. So it makes my controls a lot simpler. But now you're thinking, Spencer, how in the world can I comply with ASHRAE 90.1 now? I'm bringing something new to the table to where, where I thought I had to have some sort of waterside economizer. And that isn't the case. So there's really three paths in ASHRAE 90.1. And these three paths consist of a simplified approach, a prescriptive path, or what we like to call as the mandatory approach, and the non-prescriptive path, or better known as the energy cost budget method. And the simplified approach is simply a simple checklist that has a base set of requirements. And these are commonly used for smaller commercial buildings. We're talking less than 25,000 square feet of real estate. But this simplified approach helps alleviate some of the requirements that don't apply to these smaller buildings that it does within the prescriptive path. So the prescriptive path is primarily used for larger buildings and buildings with more complex systems where the simplified approach option doesn't apply. We're talking multi-zone buildings or buildings with central plants. And they're going to start to evaluate the equipment efficiency as well as some general requirements for the building. And lastly, the engineering cost budget method. And this is where this new design falls into play with. So the engineering cost budget method is for designers that want to explore and design alternatives, get creative, and push the efficiency levels of these buildings a bit more. So the energy cost budget, again, is for exploring design alternatives, as well as if you are not able to meet some of the prescriptive requirements just based on your building type, then you have to perform the energy cost budget method. And this allows trade-off between various building systems and components. So typically this is done with computer simulation. So a computer program is used to calculate the design energy cost of the proposed building design, what's mentioned in the prescriptive path, and compared to your new design, what you're replacing or what you're trading off. And the delta will have to show that the energy cost budget method is more advantageous from an efficiency level, meaning that my proposed plant has to be more efficient than my prescriptive path. A good example for that is if the owner wanted to choose to install more insulation in the roof, because the reason for doing that is they're trading off window area. They were going to put bigger windows in where the codes didn't allow, but to trade off, the owner wanted bigger windows, so they put more insulation in the building to accommodate for the trade-off. So just an example of the energy cost budget method, but this is where this new design of removing waterside economizers will fall into play. And we've had many engineers throughout the country and world use the energy cost budget method a lot, and now giving them the ability to remove waterside economizers in this evaluation as well. Another note on the energy cost budget method, it really is looking at the building envelope itself, not just the HVAC system. So it is looking at insulation as the example I gave did, lights, and other components within the building. But HVAC being part of that building can be evaluated and adjusted accordingly. We didn't want to leave you empty-handed on ASHRAE 90.1. It is a lot of stuff within ASHRAE 90.1, so we wanted to help alleviate any issues. We've provided a few links that give a more detailed description about the three paths. We've also given a very good example on how the energy cost budget method was performed. So they did a simple analysis in, again, the trade-offs of removing one component, replacing it with another to make the system more efficient. And then lastly, we gave links for the ASHRAE 90.1 energy cost budget method instructions as well as the compliance report. But don't be frightened by the compliance report. It truly is a 2-page document that after the simulation has been performed, you provide your efficiency numbers of the prescriptive path versus your proposed path or proposed method. And really just comparing the two models together, showing that your new design is more efficient than the prescribed. So we get back to $500,000, and I hope everyone wants to save $500,000 on their chilled water plant alone, let alone building design. Well, when designing around the YMC squared, we bring that to the table. We're able to save upwards of $500,000, depending on your building type, of course. But for the 1,000-ton office building, we're able to save upwards of $500,000 in this example. And in conclusion, we're looking at an industry that's been very dynamic and moving towards the future in energy efficiency. And chillers being one of those key components that have taken great leaps, we want to be sure that we're providing a solution that's going to maximize your building efficiency. Saving those upfront costs is very important because we don't want to provide you a solution that's going to increase first cost to become more efficient. We're providing a solution that's going to save those upfront costs and not including the Waterside Economizer and the controls and installation associated with it. We're going to save you on annual energy costs because, as you saw in those 3 locations, they were all saving energy throughout the given year. And it has to be viewed as a 30-year life, so again, bringing that $300,000 to the table. And then simplifying the system. And I want to put a big emphasis on simplifying our system because just like cars, they're getting more complex, more controls, more electronics. If we can bring something that will save on upfront costs, annual energy costs, and be simpler in design, it's very hard to find something like that nowadays with all the electronics in a building as well as cars. So that is very key because we are providing a simpler system setup for these buildings. And bringing it back to the chiller, we are providing you the first chiller in the world that can continuously operate inverted, meaning the tower water is colder than the leaving chill. Achieving that 36-degree entering condensing water is possible. And then providing those efficiency values as before seen of sub 0.1 as low as 0.07 kilowatt per ton. And we're happy to provide ratings all day long with a 0.07, 0.08 kilowatt per ton to really bring full circle to that. Our chillers are capable of this operation. And then lastly, for some additional resources, we wanted to provide additional information about the YMC squared itself. So we have provided a link, www.york.com/Mars. Talks more about the YMC squared, its flexibilities, its capabilities that it can overcome, not just the use of removing a Waterside Economizer. It has many more applications that it can apply to. A more detailed study of this summary that was performed by Taylor Engineering can also be accessed. A recording of this webinar for future references, and I want to thank everyone that is listening to this via a recording for your input, and also some related resources, meaning the cold weather operation of cooling towers that was published by the ASHRAE journal. It discusses operation of cooling towers and how to further advance our chilled water system plants. And lastly, CPO, or Central Plant Optimization, bringing full circle, not just looking at the chiller and optimizing, but controlling all aspects of a mechanical system to the optimal point. So somewhat like the engineering analysis that was performed by Taylor Engineering, CPO delivers that in real time, giving you the controls to slow down your chiller when need be or slow down your pumps. Wherever the most efficient operating point is, CPO will find it. And one more quick note, if you do have additional questions or you are listening to this via recording and you have additional questions, please contact JCI at baymarketforce.com with your questions. And again, the team supporting here in York and other locations will be sure to get those answers to you in a timely fashion. And I want to thank everyone for attending this HPAC webinar in advance. And I'm hoping that it brings to light new technology, new advancements that our chillers are capable of, as well as our chilled water systems are capable of. And right now, I would like to open it up to any other questions. Scott, if there's any questions that have come in, now would be a great time to get these wrapped up for everyone.
Thanks, Spencer. Actually, we do have quite a few questions from the audience, so we're going to jump right in. Please note that if we don't get to your question, a representative from Johnson Controls will contact you in the coming days. Okay, our first question, can this design approach be applied to other applications?
That's an excellent question, Scott, and thank you for bringing that up. Yes, this design and this system can be applied to other applications. And I'm going to quickly jump back to one of these schematics. If we start to look at the traditional chilled water operation without a Waterside Economizer, that's just an office building supplying 44-degree leaving chilled. If you have applications where you provide higher leaving chilled water temps or upwards of 60, even 70 degrees, or have a process cooling load year-round, the YMC squared is most definitely able to adapt to these other applications. And being that the chiller can operate inverted no matter the conditions, it gives you more time spent in this inverted duty if you have higher leaving chilled water temperature. So absolutely, Scott, the chiller can most certainly be applied to other applications around the world.
Do you have eQuest files already created for this chiller? If so, can they be provided?
We do have eQuest files for this setup. I will have to talk with the engineering team here to get those into the appropriate people's hands. So we will have to discuss that further offline.
Can this chiller unload below 10% load? If so, to what extent is HGBP used?
Yes, so this chiller does have a special modification that our team here in York, Pennsylvania can most certainly place on the chiller. This YMC squared chiller can turn down to 0% with the use of a hot gas bypass valve, and can, again, determining whether the application, it can adapt to other conditions as well, but 0% hot gas bypass valve can be applied.
What is the capacity range of the YMC squared chiller?
Oh, just wanted to back up one more quick note.
Sorry about that.
Typically, a 0% hot gas bypass valve is not needed because most building loads would never drop below 10%, and 10% is standard. But getting back to it, if you do have a particular application that requires 0% hot gas bypass, we are happy to apply that to our chillers.
What is the capacity range of the YMC squared chiller?
Sure. Another great question. Currently, we have a capacity range from 165 tons all the way up to 1,000 tons, and that's based on AHRI conditions, of course. If you have a lower lift situation off design from AHRI 550, 590, you most certainly can get more tons out of your chiller, but we'll have to rate with those said conditions to determine that upper echelon of cooling tons.
What is the additional upfront cost of the chillers?
That does determine based on capacity and region, but what I'd like to point out is the first cost associated with the Waterside Economizer. I'm going to bring up this slide again. The first cost associated with the addition of the Waterside Economizer to your plant is nowhere near the increased cost or the premium that a YMC squared mag bearing chiller brings. So all in all, it's still delivering an instant payback to the chilled water plant. And to point out, there is no additional cost for this feature to operate down to 36-degree entering condensing water. It is standard across the product line.
Wouldn't weather conditions allowing 36 degree Fahrenheit condenser temperature also allow Waterside Economizer operation. The chiller should be less efficient in this case. Is the main gain to save capital costs and space required for Waterside Economizer and piping/controls?
I would say everything has to be evaluated at the same time. Yes, at colder tower water, the Waterside Economizer will still come into play, but we're delivering a system design that can eliminate the Waterside Economizer altogether and still provide a more efficient plant. But yes, if you do have an existing Waterside Economizer, like we mentioned in the slide deck, most certainly use that for your free cooling application. But if there is an increased building load or retrofit in the future, just know you have a chiller that is capable of an increased load or just working hand in hand with the free cooling heat exchanger.
Why not reduce condenser water flow rate too?
Sure. So typically how condenser water flow rate is reduced is either through a head pressure control valve where it restricts the amount of water flow through the condenser, or a variable speed condenser pump. And the reason for that is it's going to increase your condenser saturated temperature, which in turn is dealing with the lift of the chiller. So if you lower the flow rate on the condenser side, you're going to negatively impact the chiller efficiency. So you're going to increase the lift on the chiller, which is what we want to minimize altogether. So for the study, we did lock in condenser flow rates as constant, but absolutely you can throw on condenser VSDs or a head pressure control device if you're modeling these systems. So absolutely it is a possibility, and we do see it every so often applied to chilled water systems, but for this analysis we focused in on fixing the condenser flow rates.
Chiller is not inverted unless leaving condenser water temperature is less than entering condenser water temperature. Minimum chiller lift is defined as difference in condenser and evaporative refrigerant pressures. Are you proposing variable condenser flow?
Depending on the application, it may be prevalent to do VSDs or restrict condenser water flow, but for a majority of these systems around the world, we see minimizing the amount of lift being the main goal in achieving for a chiller. These are all great questions, Scott. I love the activity, and everyone's kind of thinking out of the box on this, and it's great. We had a really good time here in New York in testing this application, and it's a very neat feature, if you will.
We have time for a few more questions. What is the noise level of this chiller compared to a screw?
Significantly quieter. We've seen a lot of retrofit cases where a school, for instance, had an older water-cooled screw at a lower tonnage, say around 200 tons, and because of the noise level from a screw, it's typically the pitch of a screw compressor that makes it loud, that they weren't able to occupy the space around the mechanical room because the mechanical room was attached to the school itself. And with the YMC², they were able to reduce those sound levels and be able to occupy those spaces now. Depending on the capacity, however, the sound level does change, but we like to say below 400 tons, we can achieve 73 dBA as the loudest point. So 73 and below for around 400 and below cooling capacity for the YMC².
Can you please define lift?
Sure. So lift is the amount of work that the chiller has to overcome to produce the cooling tons for the building. And what temperatures define lift is the leaving evaporator saturation temperature. We like to typically refer to it as the leaving chilled water temperature because our heat exchangers are so efficient. There's approximately a 1 degree approach, or the delta between the refrigerant within the shell and the water passing through the shell. And then on the condenser side, what the temperature that makes up lift is the leaving condenser water temperature. We've been talking a lot about entering condensing water temperature because the industry has deemed that The entering is the variable to look at, but what makes lift is the leaving condenser saturation temperature. And again, we typically refer to it as the leaving condenser water, being that our heat exchangers are so efficient nowadays that there's a 1 degree small temperature difference between the refrigerant and the water. So the leaving of both barrels is what makes up lift.
What is the chiller's NPLV value for standard AHRI conditions?
NPLV, I wish I could go more in depth. NPLV deviates from IPLV. IPLV is setting the 85 with 3 GPM per ton, and 44 leaving the evaporator with 2.4 GPM per ton. NPLV means one of those variables changed. So it's hard to determine what the lowest NPLV value is possible without knowing the conditions. But for this example that we used today, the 500-ton chiller had an IPLV of a 307, a 0.307. Again, NPLV means either the flow rate or one of the temperatures has changed, so it's hard to determine the most efficient NPLV on a YMC squared without knowing the conditions. Sorry I can't provide a better answer, but we're definitely more than happy to run ratings if you have a certain set of conditions in mind.
Are the project economics you showed based on new construction? What about installing YMC squared chillers as retrofits to replace WSE? Does that make economic sense at all?
Again, if you already have the free cooling plane frame heat exchangers, we didn't run that economic analysis within the study, but I can imagine that the plane frame, if it can still provide some of the cooling tons to the building, that it does give some relief to the chiller, and the chiller can be used to make up the tons. But from a retrofit standpoint, again, having the confidence that both components will now work together in lieu of independent of how it was before.
Many projects require competitive alternate manufacturers. Can any other manufacturer provide this capability?
To this point in time, we don't believe anyone else can provide this inverted duty, if you will, or lowest entering condensing water of 36 degrees. To this point in time, we're not aware of that. Yes, they would need to provide a full system with a Waterside Economizer to equate to the YMC squared scenario.
All right, we have time for a couple more questions. Your example was for ARI conditions. Are there any consequences in operation or efficiency when the chilled water side is a lower temperature, i.e. using this system to build ice for storage systems?
Sure. I can talk generally about that. So generally, when we refer to a 1 degree reduction in the evaporator temperature, so I go from 44 degree leaving chilled to 43 degrees leaving chilled, that typically has an impact to the chiller efficiency of about 2 to 2.5% on the efficiency of the chiller. If it's the opposite, if I go from 44 degrees to 45, your chiller is going to become more efficient by 2 to 2.5%. And again, we get back to what makes up lift is that leaving temperature on both shelves, the evaporator and condenser. So to talk about 38 to 37 degrees leaving evaporator, it will have a negative impact on your chiller efficiency. So it will just have to be something that is taken account of if you want to start to make ice for thermal storage.
If entering condenser water temperature is 36 degrees Fahrenheit and an evaporator load is 50% and condenser flow is 3 gallons per minute per ton, and leaving our LEWT is 48 degrees Fahrenheit, LCWT is 41 degrees Fahrenheit, how does chiller operate when temperatures / press are inverted? Yes.
So Scott, that's an excellent question, and now we're really getting into the technical side of how YMC squared functions, so I love it. I'm a huge fan of these questions. So what is actually happening is, even though the water temperatures are colder on the condenser side than the evaporator, that doesn't mean the refrigerant temperatures within the shells are inverted as well. So technically, the condenser saturation temperature is still higher on the condenser than the evaporator. So it's ensuring that, again, it's all about the flow of refrigerant. If the condenser was at a lower pressure or a lower temperature, then the impeller would actually spin backwards, and that's something we do not want to do with our chillers. So it is still supplying a refrigeration cycle to where it still maintains the normal flow of refrigerant as it would at a design condition.
We have installed several YMC squared chillers on recent projects. Will all YMC squared chillers support inverted operation?
Absolutely. So we have been selling YMC squared chillers since 2010, and we have well over 1,000 YMC squareds sold around the world. And all YMC squareds have this capability of utilizing 36-degree entering condensing water. And it's due to the use of mag bearings, active magnetic bearings, as well as permanent magnet motors, and the variable orifice, the butterfly valve that we utilize on our centrifugal chillers. All make this possible.
Can you start the chiller at 36 degrees entering condenser water temperature?
Yes, that's a very good point. Is even though we say the chiller can operate inverted, the chiller can, in fact, start inverted as well. So when we talk about flexibility and capability, there really is no place this chiller can't operate at.
All right, we have time for 2 more questions. In the meantime, again, your feedback is important to us. Please click the red survey icon and complete the survey form if you have not done so already. Okay, the first of our last 2 questions. Can any other chillers achieve inverted operation?
To my knowledge, I don't believe too many chiller manufacturers have this capability, and it's all, however, it is most certainly possible with advancements in everyone's chillers, even our own. So to this point, we don't believe that there are many chillers in the world that can operate this way, to our knowledge.
Yep. Okay, and then that kind of goes hand in hand with the last question. Are there any chillers running like this in the market?
Absolutely. So again, all of our YMC squared chillers, well over 1,000 in the field, can operate this way. So depending on the weather conditions that are seen at the building, can absolutely foresee an inverted operation. And again, it's not just a cooling office building application. If a data center or a hospital utilizes higher leaving chilled water temperature, it gives more ability to operate inverted as the winter months come in.
Mm-hmm. Well, I'm afraid that's all the time that we have today. On behalf of HPAC Engineering Magazine, I'd like to thank our sponsor, Johnson Controls, for making today's event possible, Spencer for sharing his expertise, and all of you for attending. Take care.